Hey, Calculus fans. I have a viewer asking me to integrate the square root of tangent of x. I wouldn't call that one of my favorite integrals. It's not an integral, I know, but I just thought I would do another integral based off of their question. They asked me a couple. I've never really competed in like integration bees. There are these integrals that sometimes require clever techniques or whatever. I'm more of a believer in our standard techniques, meaning by parts, trig substitution, partial fractions, and trying to get to those. And our main tool to get to those things is substitution. So when I see something that looks different, I tell my students, try substitution. And when I look at this problem, there's, to me, only two reasonable tries, which is this or this. So I can tell you when I was given this integral, those are the first two things I did. And that's more of what I would like to do, rather than make a video of the most clever way to integrate this, which I'm sure there are a lot of those out there. Just how would you approach it to make progress? So I think there's too much emphasis sometimes on, all right, there's a clever way to do it, and not so much a, how would I make progress so that I could have something easier and have another way to look at it. Okay, I have a suspicion when I started doing this, and I've played around with it a little bit, that the square root was going to work better. That's from experience, because I know I have this little maneuver here, and I know that I'll get rid of the square root, and that'll make this a t squared. The downside is you got to figure out the derivative, and that might not be nice. Dt is equal to secant squared of x dx, and if you solve for dx, you get 2t. Sorry, I miswrote. This is just t. You get 2t secant squared. And that should bother you, that there's still an x hanging around. But students who've taken calculus with me know there's a maneuver that gets you out of that, which is to go back here and figure out if there's a way to get rid of your secant squared. And hopefully if you've done our technique, secant squared is tangent squared of x plus 1, and tangent squared would be t to the fourth. So to me, this is a success. We're going to end up with 2t squared, and we're going to end up with t to the fourth plus 1. And the moment I saw that, I was like, okay, that's doable. Probably not pleasant, or else the student wouldn't have asked me that, but that's doable. Okay, so that's kind of where I started. Now I found out as I started to work on it, I go, well, it's doable, but it's not that pretty in terms of what happens. I suspect that there's some clean ways, clever ways, identities to get it. But again, I'm not so much about those methods, because I would like students not to think that calculus is a bag of tricks. We have set techniques, and they make progress. Sometimes they don't give us the fastest or cleanest answer. Okay, so when I saw this, I went, this looks like a partial fractions problem, except for the fact that the denominator is hard to factor. It can be factored over the complex numbers, but in a regular calculus class, we're not usually dealing with that. And if we use complex numbers, we're going to have these i's floating around, and you would need to know a lot more content. There is something that says that every polynomial can be factored over the reals into linear or irreducible quadratic terms. I know this doesn't factor, there are no real solutions to this, because I know that t to the fourth equals -1 has no solutions, if you don't know where I'm getting that. So there's a few things I do know when I look at this, is if it's going to factor, it's going to have to factor into irreducible quadratics. And so that means I know that this factors into two quadratics. And based off of the numbers I'm seeing, I also know a few other things. So the thing I don't know is the middle term. I'm guessing they have to have opposite signs, or else how would you have all that canceling that's happening in the middle? So one's a plus, one's a minus. And I already played this game, to tell you the truth, because I had to think about this. I put an a here, and I tried to solve for a. I said, well, they got to be opposite so that all of them canceled. And then I realized there's only a few ways you can get t squared. You get t squared times 1 and t squared times 1. So I had to do a little bit of work. You get 2t squared, and you also get -a squared t squared from those two. and that needs to be 0 to match the other side. So I figured out that a squared has to be 2. So this is root 2. So anyways, the short version of that is that I figured out I could factor the denominator. That wasn't easy. Okay, so t squared plus root 2t plus 1. And then I had t squared minus root 2t plus 1. So this is just me following the standard techniques, meaning it doesn't look like anything I know, so I did a substitution that landed me in the realm of partial fractions. So I factored the denominator. It did factor into something I could at least write in terms of radicals. And then I would need to embark on a partial fractions mission. Now that's the part I started to make this video and I got stuck there because the partial fraction mission is kind of messy and there's actually a few different ideas. So I already did this as I started doing the partial fractions. And that wasn't nice. So I decided it wasn't, I was doing it in the video and then I realized this is taking too long. It's messy. So thanks a lot, whoever asked this. You put me through the ringer there. Anyways, in the end, I got these numbers. Now, part of the reason I was taking so long is normally what we'd like to do is complete the square of the denominator, but I was trying to do that as I went, thinking it was going to be great. But that ended up being messier than it was worth. So I went back and just found them normally. So at this point, we're going to split them into two problems. There's going to be negative root 2 over 2t, because that's my a there, divided by t squared plus root 2t plus 1. And then separately, I'll have this other integral, which is the square root of 2. And I still don't know, maybe that I have some small error here, because this is where I stopped before. I'm just going to go a few steps further. So at this point, we have a set technique to do this. For my students, I tell them to complete the square and then break it into two integrals. That may be less optimal here. There are other things we could do, but if you were going to complete the square, it looks worse than it is. You do half the middle squared, so root 2 over 2 squared actually is just 1/2. Subtract 1/2, you get plus 1, and this now factors. So if I was doing this, I think that's what I would have done, is I would have written, let's take the negative square root of 2 over 2 out. And there might even be a way to make the constants nicer, but then I would have had a t here. And I would have had a t plus root 2 over 2 squared plus 1/2 dt. There we go. And then over here I would have a similar thing, square root of 2 over 2, the integral. I'd have a t. I complete the square. This time it would be a negative, but everything else would be the same. So t minus square root of 2 squared plus 1/2 dt. Okay, making progress. That finally gets to a place that I have a set technique. I tell students to do a substitution, and that'll split it into two integrals we know how to do. So that will work. You'll replace this with a u, maybe I'll replace this with a v. The top will become, the derivative will just be 1, so this will just become du. I'm just trying to save myself a whole bunch of writing. This t will become v plus the square root of 2 over 2. This will become u minus the square root of 2 over 2. Hopefully I did all that right. And then I would, from there, split it into 4 integrals. Oh my gosh. This must be why there's probably other solutions online where people do clever little things to get it faster. But this is getting us there. So then I'll have this du, and then I would have minus the integral of square root of 2 over 2 u squared plus 1/2. And both those integrals we can do. This one becomes a log because you can do a substitution. So this one will become 1/2 the log of u squared plus 1/2. And this one will become, It'll be the square root of 2 over 2 on top, but it'll become an arctangent. I think it's 1 over the square root of this. So I think there's another square root of 2 over 2. And then there's arctangent of square root of 2 over 2u. I hope I did all those things right. And then I'll have a very similar thing for the other one. Almost identical as this one. So it will have a 1/2. Oh, and this is all times. I'm really trying to leave things off. So then we'll have plus square root of 2 over 2, 1/2 log of v squared plus 1/2. And then we'll have this time plus the square root of 2 over 2. And we'll have this square root of 2 over 2, arctangent, square root of 2 over 2v. Plus c. So then you'd have to track your way back through everything. Now, something like this can likely be combined and simplified, meaning those two logs can be put together. I don't know about the arctangents. Maybe there's some clever maneuvering we can do to put them together. But let's just take a look here. Yeah, so what I see is square root of 2 over 4, and I'm going to put the logs together. V squared plus 1/2 over u squared plus 1/2. Putting it over because I have this minus. And then I would have plus the square root of 2 over 2. This is 2 over 4, so it's 1/2. So there's going to be a 4 here. Arctangent, square root of 2 over 2u. And then I would have a plus square root of 2 over 4, arctangent, square root of 2 over 2v. And very likely I made a mistake there somewhere. I know that's the form. I just am wondering if I have my numbers right. So I seem to be getting square root of 2 over 4, and then all this stuff. The log. I'm just seeing how much I can simplify before I suddenly substitute everything in. And then I'll look online, see how close we got. Arctangent, square root of 2 over 2u, plus arctangent, square root of 2 over 2v, plus c. All right, let's clear some of this out. Returned to where we were earlier. Okay, so v was t minus square root of 2. So v is equal, and t was square. So v is the square root of tangent of x minus root 2 over 2. And u is the square root tangent x plus root 2 over 2. So last step, take this, replace these, take this, replace these. Now I don't know if these two can be combined nicely. I don't think so. I would need to do a lot more checking before I would trust myself there. But let's take a peek. There's, what does it give? Oh, it did a similar technique. Oh, it did a clever, I see, clever rearranging. Well, that's somebody's solution. Ooh, how did it put the arctangents together? I do see the log term. You can see the square root of 2 over 4. It somehow got the tangent terms together. I'd have to look at that a little bit. Okay, I feel like I'll bail out there. So you can see I'm no expert on clever integrals, but I do think that I'm trying to illustrate most of that problem. Oh, here we go. I knew I had one open. I just couldn't find it. Oh yeah, so someone's doing a clever identity here. Someone else is adding. This is pretty clever here. They're multiplying everything top and bottom by 1 over t squared, but then how do they go from there? Okay. So these are different techniques to try to avoid having to do the full partial fractions. Okay, here's more of the partial fractions. Here's basically what I was doing. So, yes, that's a tough problem because it's kind of messy, but I hope that I illustrated that the idea of doing a substitution is definitely one of the first things you should try, and it led to a partial fractions. It's just that the partial fractions was kind of messy. Otherwise, this would have been more doable.